Hello and welcome, dear students. The title of today's lecture is Introduction to Hydrology. Before elaborating the topic in detail, I will just provide a brief introduction about today's lecture. Hydrology is the science of Earth's water, studying its movement, distribution and quality, primarily through the continuous hydrological cycle or water cycle. This involves precipitation, evaporation, infiltration, runoff and groundwater flow. Key concepts involve understanding water's journey, like how rainfall becomes streams flow or soaks into the ground. It is important for managing these processes for resources, flood control and environmental health, often using models and studying watersheds. This lecture is primarily devoted to the fundamental concepts of the hydrological cycle and the quantification of its components. So far as the nature and definition of hydrology is concerned, the term hydrology is derived from two Greek words, hydro meaning water and logos means description or discourse, or we can say that the study. Hydrology is a science dealing with the properties, distribution, circulation of water. It is specifically the study of water in atmosphere, on the surface, in the soil and underlying rocks. The scope of hydrology is broad and comprehensive, encompasses the following major aspects. Number one, occurrence of water on the earth, which comprises of both surface water and subsurface water, that is groundwater, physical and biochemical characteristics of water, distribution of water in the form of ponds, lakes, streams and earth's surface, aquifers in the underlying rocks, oceans and seas, and in the atmosphere in gaseous form, that is the water vapor, and movement of water through processes such as surface runoff, infiltration, interflow or base flow, capillary rise, stream flow and discharge. And lastly, the process of evaporation and precipitation. C.O. Whistler and E.F. Bretter in 1949 emphasized the practical and applied aspects of hydrology in their definition, which is as hydrology is the science that deals with the processes governing the depletion and the replenishment of the water resources of the land areas of the earth. It is concerned with the transportation of the water through the air, over the ground surface and through the strata of the earth. It is the science that treats various phases of hydrological cycle. The above definition incorporates additional dimensions within the scope of hydrology, including processes both natural and anthropogenic, which are responsible for the depletion and replenishment of the water resources, and different phases of water cycle such as evaporation, transpiration, condensation, precipitation and re-evaporation. H.S. Naga-Bhushnia in 2001 regarded hydrology as an applied science and employed the term hydrosphere in a broader sense to include all forms of water, solid, liquid and gaseous, present on the land surface, within the subsurface strata and in the oceans. He defined hydrology as hydrology is the applied science concerned with the water of the hydrosphere in all its states, including its occurrence, distribution, circulation through continuous hydrological cycle of precipitation, consequent runoff, stream flow, infiltration, storage, followed by evaporation and reprecipitation. Hydrology is dependent on allied sciences such as meteorology and climatology, physical geography, agronomy, geology, geomorphology and hydraulics. Water in streams and lakes, precipitation and snowfall, snow and ice on land and water found in soil and rock pores beneath the earth's surface, all topics covered by this science. More broadly, hydrology is interdisciplinary field and includes fluid mechanics, chemistry, physics, meteorology, geology and statistics. In essence, hydrology is an applied science The subject is frequently divided into these categories to highlight its practical nature. Number 1, scientific hydrology. This branch mainly deals with the theoretical and academic aspects of hydrology. Number 2, engineering or applied hydrology. This branch focuses on engineering applications related to water resources. It addresses these topics. Number 1, water resource estimation and assessment. Number 2, hydrological process research including precipitation, runoff, evapotranspiration and their interactions. Number 3, evaluation of hydrological issues such as droughts and floods and their management. Now we will look to the history of hydrology. Since history, humanity used water resources that are accessible to them. There are many examples of societies that prospered when dependable water supplies were available and fell apart when they were not. There are numerous allusions to groundwater availability and use in the Vedic literature. The Indus Valley civilization was aware of groundwater development through wells and as early as 3000 BC. According to archaeological digs at Mohenjo-daro, the hydrological cycle was understood throughout the Vedic era. According to references found in the ancient Hindu texts, the Arthashastra by Chanakya around 300 BC has the oldest account of the rain gauge and its use. The rain gauge, wind vane and rainfall prediction techniques are described in detail in the Varahimara's Brihastha Samhita around 505 to 587 AD. Records of the Nile River phases from 1800 BC have been found, indicating that the ancient Egyptians understood the value of measuring the river stages. On the other hand, Europe did not learn about the hydrological cycle until approximately 1500 AD. Cho classified the historical development of hydrology into 8 distinctive periods. Period of speculation, which is prior to 1400 AD, period of observation, which is around 1400 to 1600 AD, period of measurement, which is around 1600 to 1700 AD, period of experimentation, which is around 1700 to 1800 AD, period of modernization, which is around 1800 to 1900 AD, period of empiricism, which is around 1900 to 1930 AD. Then period of rationalization, which is around 1930 to 1950. Then period of theorization, which is around 1950 to present. So the evolution of hydrology from early speculative ideas to modern scientific approaches can be summarized through its major developmental stages. Hydrology is considered a relatively new science because the majority of its current state has emerged since 1930. The discipline's growth has basically accelerated due to its large part of rapid expansion of water resource development activities in both developed and developing nations. It also developed due to the improvements in the computational facilities for data analysis and instrumentations for data acquisition. So far as the scope and relevance of hydrology is concerned, hydrology is an interdisciplinary and applied science, as it is closely related to numerous natural sciences, human activities and biological communities. Being a broad science, hydrology draws upon several branches of knowledge, the interdisciplinary nature and linkages of hydrology with various scientific domains. As an integrated discipline, it depends on various fields. Atmospheric science is one of the fields, meteorology and hydrometeorology is another field, climatology, earth sciences, geology and geohydrology, geography, geomorphology, which includes potamology, that is the study of running water and surface streams, cryology, which is the study of snow and ice in glacier and periglacial environment, limnology, which is the study of lakes and inland water bodies, biological sciences, plant ecology, silviculture, biohydrology, hydrobiology, It also uses the sciences and knowledge of other fields like allied sciences, agriculture, forestry, horticulture, social science, hydroeconomics, that is the economics of the water resources, political science, where we study the water laws and policies, administrative boundaries at district, state and international levels, and the water related disputes. Sociology, where we study the relationship between water, human communities, including water demand, supply, utilization and misuse of water resources. And the managemental aspects, likewise we have the watershed management or the management of water resources, including exploitation, utilization, disposal of used water and the treatment of wastewater, water harvesting, pollution abatements, flood control measures, and the control of erosion and sedimentation, particularly reservoirs and lakes, siltation and riverbed sedimentation. Again, we can use the river training and channel management. So it is evident that the scope and subject matter of hydrology are wide and varied. Consequently, this is of immense importance to both human society and biological communities. So the science of hydrology is particularly valuable in varied spheres. Hydrological data on evaporation, precipitation and infiltration within a watershed provide valuable information on the probable intensity, magnitude and frequency of flood hazards. It enables planners, administrators and engineers to design effective storm drainage, culverts and divergent channels for the removal of excess water from waterlogging areas. Hydrological data and forecasters assist administrators in regulating the movement of people in order to prevent impending disasters. A notable example can be just taken from June 2013 disasters in the Alaknanda, Pindar and Mandakini river basins of Uttarakhand. The failure to act on the advance warnings issued by the Indian Meteorological Department regarding cloudbursts and heavy rainfall led to severe losses. Hydrological information, including the occurrence and yield of water, is essential for the structural design of reservoirs, dams, hydroelectric power plants, urban water supply systems, and river navigation facilities. Groundwater development and management requires a sound understanding of hydrogeology to estimate groundwater reserves, knowledge of pedological characteristics such as soil moisture, porosity, permeability, soil profiles, underlying rocks, groundwater movement, and storage in aquifers is essential for effective groundwater management. Data related to the types, intensity, duration, and frequency of the rainstorms, runoff and overland flow, and infiltration are prerequisites for assessing soil erosion. Based on such information, appropriate soil conservation and erosional control measures can be planned and implemented. So far as the decision is with regard to types of irrigation and farming practices such as irrigation, intensive farming, dry farming, sprinkle irrigation, which requires detailed hydrological data. It also helps us in designing methods of irrigation and understand the availability of the surface water and groundwater resources. Understanding the nature of erosion, whether geological, anthropogenic, along with the runoff and sediment transport processes, enable planners to adopt suitable measures to minimize siltation in reservoirs, lakes and river channels. Knowledge of groundwater potential and aquifer characters assists engineers in determining the appropriate spacing, number and depth of wells and bore wells for domestic use, for urban water supply and irrigation purposes. Knowledge of marine hydrology is useful in assessing the potential of tidal energy and in the installation of tidal power generation plants, such as which we see in the Bay of Khambhat. It provides valuable information on alkalinity and acidity of the soil and water. Processes such as elevation and capillary rise determine chemical conditions within soil and subsurface stratas. Hydrologists and civil engineers contribute to the development of the suitable structural designs for water harvesting systems and facilitate the replenishment of the groundwater aquifers. So far as the subdivisions of the hydrology is concerned, the science of hydrology is divided into several subdivisions, or we can say that are branches of different bases such as spatial consideration, characteristic features and levels of analysis. The subdivisions based on spatial considerations, hydrology is an applied and interdisciplinary science involving disciplines including atmospheric science, that is the meteorology and climatology, earth science, that is geology and geophysics and geography, soil science, physics, chemistry, biology, agronomy and social sciences. Consequently, there is a wide range of requirements for hydrological knowledge and data for different purposes. Disciplines, spatial scales, temporal scales and the locations. Based on the spatial locations and the scale, hydrology is again subdivided into various major subdivisions like surface water hydrology. Surface water hydrology is primarily focused on the study of water resources occurring on the land surface of the earth. Surface water exists in different spatial units, each having distinct characteristics such as rivers, lakes, ponds, reservoirs and wetlands. Lake hydrology is also called limnology, which deals with the study of hydrological processes within lakes. Lakes are broadly classified into tectonic lakes and glacial lakes. Some lakes are formed due to the recession of the seas and are therefore basically saline in nature. The inflow of water into lakes occurs through precipitation, meltwater, spring water, seepage water and surface streams. The Black Sea receives inflow from rivers such as the Danube, the Dnieper and the Dniester, while the Caspian Sea receives inflow primarily from the Volga River. The Great Lakes of North America, namely Superior, Michigan, Huron, Erie, Ontario, which they receive basically water through precipitation and meltwater and inflowing surface streams. Lake hydrology involves the study of processes such as evaporation from the lake surface, precipitation over catchments, circulation of water, seepage, percolation, waves. It also involves inflow through surface streams, outflow through rivers and the computation of water budget and the quality. Watershed hydrology, also known as the drainage-based hydrology, is concerned with the study of rainfall, runoff processes and stream flow within a basin. This branch is of great significant importance to human society and biological communities. A watershed, also referred to as a drainage basin, which represents the catchment area of a stream that receives all runoff generated from the precipitation within that area. Watersheds vary in size, shape and spatial scale. The watersheds are basically classified into various categories: subwatershed, milliwatershed, microwatershed and mini watershed. The shape is an important aspect of watershed morphometry. Drainage basins may exhibit various shapes such as pear-shaped, circular-shaped, elongated-shaped or triangular, depending on the geological structure, topography and the stage of landscape evolution. Watershed hydrology involves the study of aerial extent and relief drainage systems, precipitation, evaporation, transpiration, infiltration and surface runoff. It also includes the study of channel morphology, stream flow and discharge, sediment transport, as well as the influence of the human activities. Groundwater hydrology, also known as subsurface water hydrology, is a very significant branch of hydrology. It deals with the valuable water reservoirs stored in the underlying strata in the form of aquifers. Groundwater is extensively used for various purposes, such as we use it for domestic purposes, urban and rural area irrigations, crops and orchards, and as drinking water for the livestock. Groundwater hydrology encompasses the study of various aspects like the occurrence and distribution of groundwater and assessment of groundwater budgets, movement of groundwater and principles governing groundwater flow, hydraulic properties of geological materials including porosity, permeability, and hydraulic conductivity, infiltration and percolation of subsurface water from precipitation, stream beds, and the bottoms of lakes and ponds through different geological strata. Storage of groundwater in wide sand aquifers, aquifer characteristics, types of aquifers, and aquifer parameters. Manifestations of groundwater such as springs, hot springs, seepages, and artesian wells. Groundwater table levels and their seasonal long-term fluctuations. Quality of groundwater, groundwater exploitation and utilization, groundwater pollution, its control measures, and sustainable groundwater management. Marine hydrology, all forms of water present over, on, and under the earth, including atmosphere, lakes, ponds, rivers, groundwater, and the water of seas and oceans, are collectively referred to as the hydrosphere. The earth is divided into two major order relief features, the land surface and the lithosphere, and the water surface or the hydrosphere, also known as the oceanosphere. The branch of hydrology that focuses on the oceanic and marine waters is known as the marine hydrology. Marine hydrology deals with the study of ocean water, its thermal and chemical properties, evaporation forms, the oceans, precipitation over oceans, circulation and movement of seawater, and related oceanic processes. Hydrometeorology is basically the interdisciplinary branch of hydrology that integrates both hydrological and meteorological aspects. It focuses on the mechanism governing the transfer and exchange of water and energy between the Earth's surface and the atmosphere. This includes interactions between the atmospheric processes and water bodies, such as lakes, ponds, surface streams, soil moisture, and seas and oceans. Hydrometeorological processes involve heating of land and water, evaporation, transfer of heat and water within the lower atmosphere, and condensation and precipitation in the different forms. Hydrometeorology also encompasses the study of the vertical structure of the atmosphere, insulation and air temperature, general circulation of the atmosphere, atmosphere-ocean interaction, adiabatic heating and cooling, atmospheric humidity, that is the absolute and specific and relative humidity, evaporation and condensation, cloud formation, and extreme events such as cloudbursts. So far as the applications of the hydrology is concerned, the application of hydrological principles, theories, equations, and models are wide range and play a vital role in assessment, management, and monitoring of the water resources on the planet Earth. Major applications of hydrology include determination of the water budget, water reserves, and water balance at regional as well as the global scale. Estimation of the water availability for various human and ecological uses through the computation of total precipitation and losses due to evaporation, transpiration, and infiltration. Next use is the prediction, monitoring, and mitigation of the hydrological hazards such as floods, landslides, and droughts, along with the formulation of the flood control measures. Estimate of agriculture water balance based on the availability of the water from different sources like rainwater, groundwater, canals, lakes, and ponds. The irrigation requirements of crops under different farming systems such as irrigation intensive farming and dry farming across diverse climatic regions. Also, the design and management of irrigation schemes for different agroclimatic zones to enhance the agricultural productivity. The development of catastrophic models for natural hazards which originate from atmospheric processes. Similarly, prediction of riverine changes resulting from fluvial erosion by river coastal erosion, by sea waves and accelerated soil erosion, and formulation of the appropriate riparian restoration and soil conservation measures. The provisions of safe drinking water to urban and rural population from various sources including surface water bodies and groundwater. Design of dams and reservoirs for hydroelectric power generations and barrages for water supply purposes. The selection of suitable sites and designs of bridges and culverts. Design of sewerage and stormwater drainage systems, particularly in the urban areas. Assessment of the impacts of environmental change caused by the human activities such as deforestation, construction, urbanization, industrial pollution, and mining on water resources and the storage systems. And the evaluation of the extent of water pollution in lakes, ponds, rivers, groundwater and seawater. The preparation of guidelines for the rational use of water resources and the prevention of the contamination of the available water supplies. Planning and implementation of the wastewater treatment projections for urban and industrial effluents, including the reuse of treated wastewaters. And last is the development and promotion of water conservation techniques such as water harvesting, especially in the urban areas. So dear students, this was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.